Welcome back, dear students. This is Mr. Mundhe TZ. Welcomes again all of the Bsc T students in the class of chemistry. And today we are continuing the same topic, that is coordination chemistry part first. In last lecture we had seen what is meant by coordination chemistry, what is meant by double salt, coordination compounds, then the terms used in the coordination chemistry. All those we have seen, and then we have gone for the types of ligands. We had gone for the types of ligands. Now we will continue the types of ligands. See at the screen, the first type of ligands is monorental ligands. As I have told in previous lecture that the ligands have been classified into different categories based on their nature or based on the denticity of ligands. Both classifications are of important, but for your level you can go for the classification based on the denticity. So the first type is monodentate ligands, or you may say it as unidentate ligands. So what are unidentate ligands? You know that ligand is a species or group of atoms or atom that donate a pair of electrons to the central metal ion. Ligand is a species that donate a pair of electrons to the central metal ion. Now based on this denticity, it means if atom is monodentate, at that time it can donate just 2 electrons to the central metal ion. If a ligand is biodentate, at that time it can donate 4 electrons to the central metal ion through 2 sides. So the monodentate ligand means nothing but the ligands that can bond with the central metal ion through only one donor atom is known as monodentate ligand, or you may see it as these have only one donor atom, or the monodentate ligands have only one donor atom, so that they can donate through only one atom. And these are examples are carbon monoxide, cyanide ion, NH2, OH group, H2O. All these are the monodentate ligands. For example, in case of H2O, only oxygen has 2 lone pair of electrons that can be donated to the central metal ion, and one of the lone pair of electrons is donated by the oxygen atom, and the H2O is a monodentate ligand. Now the next is biodentate ligand. The ligand that have ability to bond with the central metal ion through 2 sides or through 2 atoms is known as biodentate ligands, and you can say these have 2 donor atoms, or the ligands that have 2 donor atoms are known as biodentate ligands. And the example is ethylene diamine, So the next example is oxalate ion. Similarly, you can go for further examples in the reference books. Then the next is polydentate ligands. The ligands that can bond with the central metal ion through more than 2 atoms are known as polydentate ligands. And you can also say that polydentate ligands have more than 2 donor atoms, and the example is EDTA. What is EDTA? Ethylene diamine tetraacetate. Is EDTA. Okay. Now see. The next is ambidentate ligands. The ligands that can bind with the central metal ion through one or more donor atoms, but it bind with through only one atom, are known as ambidentate ligands. It means a ambidentate ligand is that which has two donor atoms, but at the time of bonding it can bond through only one atom, so that these are known as ambidentate ligands. These are known as ambidentate ligands. And you say it has these ligands have two donor atoms and can form bond with central metal ion through any one of donor atoms are known as ambidentate ligands. And the example is carbon monoxide, and the example is carbon monoxide. Also along with this carbon monoxide you can say sulfate ion, SO4 dinegative ion, then Cn minus ion, and then your NO ion. All these are ambidentate ligands. Then the next is chelating ligands. The ligands that can bond with the central metal ion through two or more atoms to form a ring-like structure are known as chelating ligands. The ligands that form rings with the central metal ion are known as ambidentate ligands. Okay, and the example is are known as chelating ligands. And the example is EDTA or diethylene triamine, or you may say it as triethylene tetraamine. Any example you can take, okay, that can form a cage. Chill means claw or cage, and chelatin that is like crab, that of crab. You can see that the complex looks like a cage, so that these are known as chelates. The complexes are known as chelate complexes. So the next point is, after looking into all the terms that are involved in the coordination chemistry, now we will go for the nomenclature of coordination complexes or coordination compounds. But before that, see here, CO, which is to be shown in green, that is a central metal ion, that is cobalt plus 2 is a central metal ion. Then whole term that is covered in the square bracket from our upper side, that is a coordination pair, or you can say it as complex ion. The Cl2 and NH3 are ligands. Cl2 and NH3 are ligands. Then the Cl2 and NH3 also show the coordination numbers, and there is formal charge also. Okay, now after looking into this, we will go for the next is nomenclature of coordination compounds. Now see, many compounds exist in this universe, and similar to that of many peoples exist in this universe, but each man or each existing man in this universe has a particular name. Similar to that, we must make names or give names to the chemical compounds also. We had a similarly seen in the organic chemistry in 11th standard, then Bsc FY also, the nomenclature of organic compounds. Similarly, today we will see the nomenclature of inorganic compounds, or coordination compounds. Okay, there are some rules for the nomenclature of coordination compounds as shown in the as seen in the organic chemistry, and these are rules that can be followed while giving a name to the inorganic compound. Now see the rules. The first rule is, the name of the compound is written in two parts. The first part is name of cation and the second part is name of anion. The name of any coordination compound can be written in two parts. One is cationic part and another is anionic part. The second rule is the cation is named first in both positive and negatively charged coordination complexes. Second rule is that the cation must be preferred, or cation must be written at the left hand side. The cation must be written at the left hand side, or firstly cation should be given name. Then the next is the dissimilar ligands are named in alphabetical order before the name of central metal, atom or ion. If a compound contains different ligands, then we may consider the alphabetical order of these ligands for the nomenclature of the ligands. Okay, consider that if your complex contains hydroxy group, then amino group, then chloro group, at that time, or you may say it as cyano group, at that time you have to go in the alphabetical order. Firstly consider your complex contains amino group, then chloro group, and along with that your bromo group. At that time you make take the name of firstly name of amino group, then bromo group, and then chloro group. Okay, in this fashion, if your complex contains more than two or more ligands, at that time you may nomenclature and name to it in alphabetical order. Okay, then for more than one similar ligand, the prefixes di, tri, tetra, etc. are added before its name. If the di, tri, etc. already appear in the complex, then bis, tris, tetra keys are used. It means if your complex contains more than two or more same ligands, at that time we must use di, tri, tetra prefixes. For example, if the two amino groups are present in the same complex, at that time we say it as diamino. If 4 chloro groups are present or 6 chloro groups are present, at that time we say it as hexachloro ligand, then or hexachloroterm. Then the next is, if these terms di, tri, tetra are already used in your ligand at that time, and the term is being repeated again, at that time we must use bis, tris, tetra keys terms. Okay, now the next is, if the complex part is anion, the name of the central metal ends with suffix ate. If your complex part is a anion, it means it carries a negative charge. At that time, the ending of the complex name will be with ate suffix. Ate suffix must be added to the name of the metal in case of anionic complexes. The next is, the names of anionic ligands end with O, the names of positive ligands end with IUM, EM, and the names of neutral ligands remains as such. It means there are three types of ligands, as I said previously, and these are cationic ligands, anionic ligands, and neutral ligands. If a ligand is negatively charged, at that time it should be its ending should be as O. For example, if your complex contains chloride ion, at that time it should be considered as chloro. If your complex contains amine ion, at that time it should be considered as amino. If your complex contains hydroxy group, at that time it should be considered as hydroxo. Similarly, if your complex contains a positively charged ion, the ending should be IUM. For example, in case of hydrazinium ligand, the ending should be hydrazine ligand, and the ending should be hydrazinium. It means IUM must be added to the added as a suffix in case of positive charge ligand, and the names of the neutral ligands may remain as it is. As you have to just put the names of neutral ligands as it is. Then, but there are some exceptions to the neutral ligands. For example, if the ligand is water, at that time we say it as aqua. If the ammonia is the ligand, then we say it as amine. If the carbonyl group is the CO, carbon monoxide is the ligand, at that time we say it as carbonyl. And if the NO, nitrogen oxide is the ligand, at that time we say it as nitrosyl. So there are some exceptions to the neutral ligand, so you may mention, or you have to mention the names of the these neutral ligands. That could be better for your syllabus. The next rule is oxidation state for the metal ion in cation or anion or neutral coordination compounds is indicated by Roman numeral in parenthesis. See, the central metal ion carries some charge, or it has lost some electrons, so that the number of lost electrons lost by the central metal ion is known as oxidation state of that metal ion. And this metal oxidation state of that metal ion can be written in Roman in parenthesis. So you have to just write this oxidation state in parenthesis in the Roman numerals. Okay, the next is the name of the complex part is written as one word. The whole complex name is written as a single word. The whole complex name is written as a single word. There should not be any space or any gap in between the two words. Okay, it should be a single word. The next is, if the complex is a cation, the metal is named same as the element. See, if the complex, as we have seen in case of anionic complexes, the name of complex end with the et, but in case of positively charged complexes or cationic complexes, the name should be as it is as that of metal name. Okay, the next is the neutral complex molecule is named similar to that of the complex cation. Also, the name of neutral complex is similar to that of metal. Okay, there is no need to add any suffix. Okay, and there are some examples of these coordination complexes. So the first example is, see here, there are some metals and some ligands that are shown here. In the first example, chromium is here, ammonia is here, H2 is here, and also your chlorine is here. Then how to make the names of these or how to give the names of these ligands, coordination complexes. See here, here there is a chromium metal ion, so that should not be considered initially. There is no cationic part, so it should not be also considered. See, there are two ligands, and we must consider the alphabetical order, so that, see, amine, triamine will come first, triamine, triaqua, trichloro, chromium, third, chloride. This is the name of this complex. Triamine, triaqua, chromium, third, chloride is the name of this complex. Here is one mistake while typing. You must consider it as triamine, triaqua, chromium, third, chloride. By mistake, I have used trichloro instead of triaqua. So note that here, triamine, triaqua, chromium, third, chloride may be considered here. Okay, the second example is cobalt complex. See, the name of the complex is tris, ethane 1,2 diamine, cobalt third sulfate. See here, we have already used the amino groups, so that the amino group is being repeated, so that we have used the di term, and now we also have to use the tri term also, so that we have used a tris. Okay, tris, ethane 1,2 diamine, cobalt third sulfate is the name of this complex. Then the next complex is a coordination complex, and that is this complex is diamine silver first, dicyano argentinate first. See here, there are two parts, one is cationic part and another is anionic part. So that we have considered firstly just cationic part, and then we have considered anionic part, and the ending of the anionic part is with ATE. Okay, so the name of the complex is diamine silver first, dicyano argentinate first. The next example is K4FeCN6, and the name of the complex is, it also consists of two parts, one is cationic part and another is anionic part. So we have taken the cationic part firstly. So the K4 is potassium hexacyanoferrate second. Potassium hexacyanoferrate second is the name of this coordination complex. Okay, and there is a list, there is some list of the ligands and their names. These are negative ligands. See here, there is a long list, you can go through this list. Then there is for some positive ligands, and these are nitrosonium and hydrazinium ligands also. Then the neutral ligands also are here, the aqua amine, carbonyl, methylamine, nitrosyl, pyridine, all these are neutral amines. After completion of all the content of today's lecture, tomorrow we will continue the next. So up to, thank you, we will meet tomorrow. Thanks again.